I'm very pleased to introduce our next speaker, Felipe De Brigard of Duke University. Felipe is a professor of philosophy, a member of the Duke Institute for Brain Sciences, and a member of the Center for Cognitive Neuroscience. He also heads the Imagination and Modal Cognition Lab at Duke University. He's a very empirically trained philosopher or a very philosophical cognitive neuroscientist. He's actually both at once. His work includes some really influential work claiming that memory is not solely for remembering, but is part of a broader system in the brain for counterfactual thinking, episodic simulation, modal cognition, and he also has quite broad-ranging interests in the role of dynamics and individual differences in the brain, say with his work on aging, and is going to talk to us today about a new project that we're excited about on the mirage of big data phrenology.
Thank you, John. Thank you very much to all of you for being here. This is one of my absolute favorite places to philosophy of mind and philosophy of neuroscience. Joe, thank you so much for organizing this conference and for the people that help you, the fellow students that help you. And it's really great to see that this is the product of the summer seminars in Neuroscience and Philosophy that I co-direct with my colleague Walter Super too. And it is great to see one of the products here participating in that. All right, so this is very much a work in progress. I know that a lot of people say that before they give talks because they're not sure of the things that they're saying. This is like for sure really much work in progress. And it's actually the result of a lab meeting where we read a paper, which is the main focus on the talk today. And I should say that this is actually work that I've been doing with two of my graduate students. So we're all equal co-authors, and as I explained in the paper, the order of authors was determined by temporal proximity to the job market. So oftentimes people start the talks about cognitive ontology by referring to phrenology, but it turns out that prior to phrenology, there were all the attempts to try to link like psychological concepts to the brain. For many, many years, the traditional view, if you want, was the ventricular theory that it didn't link things to the brain, but to the ventricles. This was a nice sort of demonstration by Gregor Freysch dated in 1525 that you have memorabilia and the faculty of imagination and the faculty of the intellect, each one in one way 3 ventricles. Leonardo da Vinci also espoused something like the ventricular theory. Back in the day, the theory was a philosophical theory mainly derived from Magnus, and which in turn was derived from Aquinas, according to which these faculties of the mind were supposed to be linked somehow to parts in the brain. It's just that the parts in the brain were the holes in the brain. So prior to phrenology, there were some phrenological attempts that we don't necessarily consider phrenological. Now, phrenology, of course, is well known, especially for members of the audience. One thing that is interesting, sometimes we don't realize, is that there were lots of discussions about how to best characterize the bumps in the head and the relevant parts of the brain in phrenological discussions. This is a journal, the American Phrenological Journal, and this is the cover of 1948. And if you had some time in your hands, you can actually see that there are differences between that mapping from 1948 and this previous mapping from the Edinburgh Society in 1920. Because there were discussions among phrenologists as to whether, similar to what we're doing here, as to whether we're actually using the right categories when we're drawing the phrenological maps. And there were lots of evolutions until pretty much the turn from the 18th to the 19th century. Of course, phrenology was also employed to give advice to people as to, for instance, how to find a genuinely good husband. And I like this. This says things like, young ladies, indelibly fix the shape of head in your memories. It says, any man who will make an actual kind of true husband will have a head in outline from this side view like this. And then on the other side, the unreliable husband says, the reason this man is an unreliable husband is because he is very weak in conjugality and parental love and exceedingly strong in amativeness. Young ladies, beware of such men as husband. And it's great because they give us a definition of why people are polygamous. Polygamy is an amalgamation of amativeness, spirituality, and veneration. Strange, but perfectly true. When people started conceiving of cognitive neuroscience, I think that at the back of their minds there was this naive assumption that there was going to be something like a smooth transition from psychological terms to neural terms. So we were thinking of something that cognitive neuroscience will give us a map along these lines. You have psychological terms that somehow smoothly are going to transition into brain or neural terms. So this is an exercise that I do every time that I talk a little bit about cognitive pathologies. I go to Google Scholar and I Google the neural correlates off in the title. And yesterday I did it, and there are approximately 1,980 results that are complemented by a folk or a scientific term, such as the neural correlates of variable working memory, the neural correlates of maternal and romantic love, the neural correlates of subjective value with very intertemporal choice, sensory awareness, spider phobia, motor skill automaticity. Someone in this room published that book. I mean that article. Someone in this book in this room published that one. And fear. And this is just, I think, the first two Google Scholar pages. So the view actually is much more complex than this original transition. Almost every brain region seems to be engaged in all sorts of different cognitive processes, doing all sorts of different experimental tasks. So as Price and Princeton said it in your paper in 2005, far from being a one-to-one relation, or even a one-to-many relation, the picture is rather a many-to-many relation. And I try to capture the fact that this many-to-many relation is also likely probabilistic by changing sort of the weights of the lines. So it looks, from the looks of it, and it sounds like an impossible task to try to figure out how to map the psychological terms onto the neural terms. But is it really that difficult? Well, earlier this year in April, there was this paper that came out in Pigs, and basically the rest of my talk is going to be about this paper. Sarah Gannon is the first author from Ago's group. It is called How to Characterize the Function of a Brain Region. I don't know if you guys have read it, but if not, then maybe you won't have to, because I'm going to talk very carefully about it. And in this paper, we read it very interested. It was like, oh, look, this is amazing, man. By the abstract, it looks like, oh, finally, cognitive ontology is solved. Their argument is not so fast. It's not really an impossible task. The problem, they say, is that we have been employing a top-down approach all throughout. And what we have to do is to change the perspective in which we conduct our research in cognitive ontology. And the suggestion is that the starting point should be what they call an a priori. According to them, the way in which we have been doing it so far is that the starting point is an a priori cognitive, which they call behavioral function, like episodic memory or working memory or visual attention and so on. And then what we treat normally as the unknown is the brain region that is associated with it. But their suggestion is that we need to change, kind of like inverse the order of discovery. Instead of having as the unknown the brain region, we should, they say, start with the a priori defined construct as the brain region, and then the unknowns are supposed to be the behavioral functions associated with it. All right? I call this the bottom-up approach. So, in what follows, what I'm going to do first is I am going to sort of spell out the arguments against the top-down approach from Gannon and Al. I'm going to say there's some things that I agree with in those arguments, and there are some things that I disagree with. Then, in the second part, I'm going to reconstruct Gannon et al.'s bottom-up proposal. And what I'm going to do is that I'm going to identify a number of challenges to that bottom-up approach. And at the end, I am going to end up with a sort of a final assessment. And the final assessment is that neither the top-down nor the bottom-up alone will work, but something that I'm going to be willing to call the piecemeal approach. So we'll get to that toward the end. All right, so let's start off with a little bit of terminology from Gannon et al. The first thing is that they, for some strange reason, they talk about cognitive functions in terms of behavioral functions. And the things that they list, this is a deictic definition, if you want, rather than an account. So like these are behavioral functions, and they list the following ones: psychology-related constructs like episodic memory, working memory, motor preparation, visual attention, memory consolidation, speech production, perspective taking, and emotion regulation. That's the list of the things that they include on their behavioral function. And then there's another definition, what they call operation function, which is, according to them, a computational operation performed by a given region which contributes to the observed behavioral output. And I'll get to those later on in more detail. So their suggestion is that in the top-down approach, what we end up finding is something like a latent variable that explains or that accounts for what they call functional polyhedra. What is a functional polyhedra is the idea, as we mentioned, is that every region is associated to many behavioral functions via this latent operant function that unifies them. And this is, in their words, our current knowledge of the functional specialization of a given brain region can be conceptualized as a polyhedron with its many sides, that is, its many behavioral functions, the sum of which can only be appreciated by investigation from many different perspectives, but whose core center remains intangible. So this is, to give you an idea, I told you I would talk about the hippocampus. So let's consider the hippocampus, probably the most important area of the brain. This is my rendition of a polyhedron. So when you look at what hippocampus, or when the hippocampus is supposed to be active, you find it active in tasks that supposedly index declarative memory, associative learning, consolidation, novelty detection, relational binding, comparator tasks, spatial discrimination, prospection. So the suggestion is that all these behavioral functions are like sites in this polyhedron. They're all sort of are around this core center, or operation function, they call it. And this operation function is supposed to be able to unify all of this behavioral functions by identifying a computation that is common to all of them. And their suggestion is that this computation is that this computation will be able to account for why is it that the hippocampus is engaged in all of these tasks. So we call that the operation function of the hippocampus. All right. Now, how is this polyhedron created? Their suggestion is that typically the approach for creating this sort of polyhedron is top-down. And they go on each one of the methodologies that we normally associate with top-down approaches and then sort of criticize them. The first one is lesion deficits. Okay? So their suggestion is that lesion deficits are pretty bad to give us like really accurate accounts of the operation function because there are lots of different factors outside of the lesion that might participate in the disorder of the behavioral function. So for instance, pre-lesion factors. Also, there is another concern, which is that pre-lesion factors is the fact that prior to the lesion, the person might have had some difficulty. So HM is a very good case, and I'm going to use the case of HM a lot because I really like it. HM, as you might know, had very, very severe epilepsy. He had something like 2 or 3 grand mals per day, and the order of 20 to 30 petit mals each day. I mean, this is just incredibly debilitating. This is prior to the surgery. He was in medication, really enormous amount of medication prior to his surgery, since he was 11 or 12 years of age. So it might be possible that some of the effects could be attributed to the fact that he was already, these are like, pre-1950s medications, so the side effects might be even worse. So it might be possible that some of the effects are due to pre-lesion factors. In addition to that, some lesions are not terribly specific. HM had a lesion that was relatively, cartographically specific because it was carved, artificially. But most of the lesions that we have, when you have herpes that is accumulated in the, behind the front, the temporal lobe or what have you, is not going to respect the neuroanatomical boundaries, right? So they're not terribly specific. Now, we all agree with that, but for me, the most complicated issues with lesion deficits is that neuropsychological profiles are only as accurate as the tests you employ to describe them, right? So for instance, HM is a really, really good case. HM was tested for working memory, which was a term that was not employed until after 1968. It was tested for working memory by Brenda Milner in the 50s by digit span only. And now we have quite a bit of evidence coming from Sharon Grangnan's group to the fact that certain kinds of working memory are likely to engage hippocampal activity. So the neuropsychological profile that we get from HM is that his working memory was intact, when in reality it was only tested with one particular kind of test. We don't know if his working memory was intact for other kinds of materials. And that's just a problem of the fact that we characterize neuropsychological profiles on the basis of the tests that we have. So that's another difficulty with the lesion deficit approach that they don't discuss. The second approach, top-down approach that they discuss is stimulation. So with transcranial magnetic stimulation or variants thereof. It's messy in the sense that although it's getting much better, my colleagues at Duke now are doing this awesome emulation that really gets quite a bit of specificity in the stimulation. It is limited in the sense that there are parts that cannot be really stimulated with EMS, parts of the brain, especially for medial and ventral regions. And their suggestion is that it lacks ecological validity. I really don't understand that point that much. HM's lesion wasn't really ecologically valid, right? It's not like that normally people have an accident in which they remove exactly the hippocampus. So back in, some of you know that I have a background in neuropsychology, and I saw a ton of patients in the military hospital in Bogota, and many of those patients had bullet wounds, which are also not terribly ecologically valid. They don't respect, as it were, neurological boundaries. Another point, but nevertheless, yes, stimulation is somewhat messy. Our favorite one, activation approaches with fMRI. Interestingly, they don't discuss a whole lot of issues with fMRI, more than, for instance, there is an issue about pure insertion. How are we completely sure that we're really isolating the mental process that we're supposed to be isolating? This is a concern that is not only for fMRI, by the way. For instance, we make assumptions, behavioral assumptions about pure insertion with reaction times. So we think that in reaction times, because a thing lasts longer, then it must be the case that there is another process that came into play. But it might be possible that there is the same process just elongated, or it might be possible that there is another reason why the reaction time is longer. So it's not specific for fMRI. There is another concern, which is there might be task-specific effects that we're not really controlling for. But they also sort of don't appreciate the fact that that now we do more than just contrasts and more than univariate approaches. There are lots of multivariate approaches that take care of some of the concerns. Not all of them, but some of the concerns. And finally, they talked about structure and behavior correlations. That was similar to the talk that we listened to this morning. They criticized them on the fact that there are lack of experimental controls or alternative explanations. Sure, that's a problem that people are completely aware of that, and as a result of that, we have now multi-site experiments with control conditions, large data sets, and so on. So some of the arguments against the top-down approach are a little hand-wavy, and people are very much aware of some of these concerns. Nevertheless, we agree with the top-down approach might not be, infallible, and I think that no one in this room thinks that it is completely infallible. So their suggestion is that, look, the top-down approach is inadequate and incomplete, which we could agree. So then they say, like, look, to assess the relative functional specialization of brain region critically requires a change in viewpoint, where the a priori defined construct is the brain region and the unknowns are the behavioral functions associated with it. All right, so let's see what they mean then by this bottom-up approach. Their suggestion is that basically to do bottom-up approach, we need 4 steps. the first step is to identify a region of interest. And in the entire paper, they use just 2 regions of interest. These are 2 examples that they give us, the hippocampus and the anterior insula. The next step is to use big data. And to use big data means, combine brain map and neuroscience and whatever repository of fMRI you have there, the more the merrier. And after you use this big data, then you identify functional profiling. That is to say, not only the few papers that you have read and create a polyhedron, but actually this is like data-driven polyhedron creation. That's what they call behavioral profiling. And then, magically, apparently, you infer the underlying operational function. So how does this work in practice? Let's just give it a try. I think that something like this might happen. So you get into Neuroscience, you type anterior insula, it comes to your meta-analysis, and then you go to papers. And then it gives you a list of papers with several weights and loadings onto those factors, right? And then you sort of skim over those papers, maybe you read them, if you have the time. And then you end up finding what are the functions, the behavioral functions that they were supposed to be measuring with these papers, and then you create the polyhedron. So this is just literally from the first 12 or so of the papers that came out of the 600 and some from Neuroscience alone. I didn't even look at Great Map or other databases. So you get insula activation, preeminently engaged in tasks that involve pro-social behavior, social cognition, inhibition, which we talked a whole lot about this morning, executive function, unreciprocated cooperation, regret. And I could tell you that because I do a lot of counterfactual thinking stuff on the internet. Boom, it's like a pearl in regret. Not so much in relief, which is interesting, but in regret, a lot. Food motivation, sustained attention. So they, in the paper, sort of, they don't talk about all this profiling. I actually did this work like that. But they say that, look, insula is engaged in these things like inhibition and food motivation and sustained attention. So once you do this functional profiling, it's going to become very clear that the operation function of the insula is task engagement maintenance.
Sorry.
No. It is fine. You got it. Sure. They suggest still in its infancy, right? Maybe this is not. We're going to refine exactly what the function is. But as you aggregate more data, then the behavioral profiling becomes more precise. And the suggestion is that in turn, the identification of the latent operation function becomes more accurate. This strategy, they suggest, should help us with what cognitive neuroscientists are already doing. So let's think about, and consider the example of the hippocampus, which I will get back into. What is the hippocampus doing, for instance? This is the example that they give us. Look, when you look at tasks in which there is hippocampal activation, you find things like episodic, encoding, mental simulation, and spatial navigation. But our research strategies are limited, right? You cannot read everything. I can barely read anything anymore. You cannot read everything that there is, so let the big data read for you, as it were. And then once you combine this with big data, then you end up with a much more comprehensive behavioral profiling. Perceptual, now you know that the hippocampus is engaged in some kinds of perceptual discrimination, statistical learning of higher order properties. I heard last weekend Nick Brown showing incredible data showing statistical learning of high probabilities in 6 months in infants. Hippocampal activation, you know, statistical learning, self-referential counterfactual thinking, which we do a lot in the lab, and consolidation of motor sequences. And once you have this much more comprehensive behavioral profiling, then the operation function will become clear. That's the idea. So their suggestion is this daunting picture that we started off with might become much more manageable if we think of this intermediate level as a level of operation function that emerges as a latent variable for this behavioral profiling. All right. What I want to do now is to offer a series of challenges. Philosophers might call them objections. I'm in between, so I'm just going to call them challenges to the bottom-up approach. I'm going to talk about three, but I have a couple of others on my side. The first challenge is that it's very difficult to understand what's a brain region. So they suggest that we should start with the a priori notion for brain region. But what's a brain region? So, and this is interesting because I'm quoting this from Akos himself. So like, there are many ways to demarcate basic, what he calls neurological atoms, or sometimes he calls them brain atoms, associated with latent operational functions. So let me give you a little bit of neuroanatomy lesson. Well, some of you probably know way more about this than I do, but let's consider the anterior insula. You don't move. This is a poor brain without the operculum. You sort of open up a whole bunch of brain, and then you release the insula, and then you see this structure. So the insula has been identified as having three areas relatively well demarcated by the sulcus circularis. Sorry for the typo, sulcus circularis. And the insula in general, according to this estimate by Newland-Lewis in 2012, covers about 2% of the total cortical surface, which is amazing given how many times the insula is activated there. Because of Brodmann's original site for architectonic mapping in 1909, we divide the insula into posterior, mid-insula, and anterior insula. This is the original rendition of Brodmann's one patient. And then you can see, this is his original drawing actually, different site architectonics in the anterior insula and the relative to the posterior insula. This is a more contemporary rendition of the insula that sort of depicts the degree of granularity in the layers by just how many little dots you see in each region. And this Brockhaus map of the insula clearly identified two parts of the anterior insula: the rostroventral agranular zone and the caudodorsal granular zone. Basically, the main difference is that layer 4 is almost absent or very much present in this in one region versus the other. So you will see here there is almost no layer 4, and the layer 4 has a lot of space between neurons. So they call it agranular because it's not terribly punctagistic. Whereas the caudodorsal granular zone has a much more concentrated amount of neurons in the fourth layer. Now, here's an interesting fact. This little bit of the insula, of the ventricular zone of the insula, is about 2 cubic centimeters, right? Now, depending on your scanner, some of you have better scanners than I do, that goes from the order of hundreds to maybe even 1,000 of your typical isotropic functional voxel. And by recent estimates, each one of those voxels opposes to a typical 2 by 2 by 2 is something in the order of 630,000 neurons per voxel, right? So the question is, there's a bunch of voxels in that tiny little bit. We saw the depiction of the insula that you showed earlier this morning, that must have been something of the order of 80 to 100 voxels. So the question is, do we have any reason to believe that all the fine brain neuroanatomical operations of the anterior insula happen to converge in a single operation function that we call task engagement maintenance? Right? And so here are more problems with how to define brain regions. Some psychoarchitectonic borders are incredibly poorly delineated. We know this we neuroimagetors know this, that some cortical boundaries are much more complicated to identify than others. So if you go to the visual cortex, which is people's typical example, usually the columns end up kind of like right next to one another, like little houses that they have like divisions right next to one another, and cortical parcellations are relatively easy. But that's not so around the brain, especially as you move outwards of sensory cortices. The brain becomes much more interpolated, and like the neurons that in one region end up innervating regions in neurons in another region, and those boundaries become messier. And some of these boundaries becoming messier are actually very complicated because, for instance, there are disagreements among algorithms for cortical proselytion. The anterior cingulate cortex is one of my favorite difficult disagreements. So Jonathan Powers from here had one particular resolution using, I think, a snowballing algorithm. And then there are other, but the Pan-African group, Pan-African group had a different resolution. So there are specific small regions in the brain where the cortical proselytion becomes really, really difficult, in part because the acceleratory borders are not clearly delineated. But in addition to that, not only the brain seems to be in disagreement, researchers have in disagreement as to when a certain region ends and another one begins. Here's one awesome paper. It's called Broca and Wernicke Are Dead, or Moving Past the Classic Model of Language Neurobiology. This is Gershwin's depiction, textbook depiction of Wernicke's areas and Broca's areas. So here we have a massive amount of brain that is supposed to be in Wernicke's area. This archifascicle, a little bit too contorted to that in my case. This region between the pars opercularis and the pars triangularis that we normally identify as Broca's area. Now, what the authors of this paper that I shouldn't have included here did is that they looked at all the depictions of Wernicke's area, basically since Wernicke's own depiction. And what they find is that there is an enormous amount of disagreement as to where Wernicke's area is supposed to be, right? So these are the authors' definition: Gershwin, Penfield and Roberts, 59, Jejerin, Wernicke himself, Lewandowski, and Nielsen. You see, there's a lot of variability here. I couldn't find a slide when one of the SFNs recently, Uriel Messerman presented a heat map of brain axons of a bunch of patients that had, exact, precise clinical diagnosis of Wernicke's aphasia, or I guess, not production aphasia, understanding aphasia, right? And the heat map was like everywhere in the temporal cortex. My favorite result of those that he presented was flabbergasted at that talk, is that the most clear case of Wernicke's aphasia that he presented had one small axon in the tip of the temporal lobe. It's like, what? That's far away from Wernicke's area, right? Broca's area doesn't get any better. That's the definition I learned, is the area between the pars opercularis and the pars triangularis. But if you ask people, say like 50% of them say that around here, there, this one includes the pars triangularis, that one is only the pars triangularis, that one is only the pars opercularis, and with 2 or 1 sulci. So there's a lot of disagreement even among neuroscientists as to what is exactly the limits of a brain area. And just to drive the point home, there are even more problems. Because it is possible actually that for many operational functions, the brain regions involved might not even be topographically unified, right? They might instead consist of discontinuous bits of tissue working together. This is the point that Fox and Kristen made in your image, right? And this is what happens if that's the case. We started with this sort of solution to the mapping, but if we break down the brain region into actually like the components of that brain region, we might end up finding that they actually don't correlate one-to-one to this operation function, right? And if they don't correlate one-to-one with this operation function, then the one-to-one between brain region and an operation function just basically breaks down. So the question is, but why did Gannon et al. Pick the anterior insula and the hippocampus as examples of basic brain regions? I mean, they're not bad neuroscientists or anything like that. Why did they pick it? Well, my hypothesis is that they did it for 2 reasons. The first one is because of the resolution of instruments and methods. That's one. When you have a hammer, everything looks like a main. But the main reason is because we have theories that tell us that those are presumably good candidates for basic brain regions. But if we have theories that tells us which ones are the best candidates for basic brain regions, then the notion of brain atom is not a priori, as they suggest it is. All right. A second objection, challenge to the view. Operation functions are always model dependent. It depends on what is the model according to which you want to interpret. So when you read the paper, it seems to be that Gannon et al. Actually kind of mischaracterized the way in which cognitive neuroscientists normally, from the top down as they call it, normally attribute operation functions to brain regions. So let's again consider the hippocampus. Most important part of the brain, of course. So here's the received view. Prior to HM, we had some idea that the hippocampus was engaged in spatial memory because of rat work. And also it was very, very clear that it was engaged in some sort of olfactory processing. That was the thought, because the olfactory bulb is like right underneath the hippocampal complex. So with some nuances, Penfield disagreed with Scoville about this one, but prior to the accident, the surgery with HM, it was pretty clear that he was probably going to develop an anosmia. That is to say, he was incapacitated to recognize smells, which he did. He was completely anosmic after the surgery. But of course, HM provided an enormous amount of information about the hippocampus being engaged in certain tasks. So originally, thanks to animal studies and neuropsychological data and well, forget about the pet studies at that time because they hadn't happened, we had the thought that the hippocampus was engaging in memory. But then you did subsequent tests with HM, with other patients, then other techniques that started to appear, and it was very clear that, or we thought it was very clear, that it was not all kinds of memory, but only declarative memory. And then further tests and further refinements, it turns out it's not every process in declarative memory, but definitely encoding at the very least. And then there's more recent amendments, and then you have other groups that have shown that the hippocampus seems to be engaged in certain kinds of imagination, like, for instance, episodic future thinking, but not apparently with other kinds of imagination, like semantic future thinking. It seems as though you can talk about the future of the United States in the next election if you don't have a hippocampus, but you cannot really talk that much about what you're planning on doing for Christmas if you don't have a hippocampus. Also perception, one of my, I think, favorite results in the role of the hippocampus, the hippocampus is the end of the ventral pathway. And one would imagine that there's some ventral visual pathway, and then one would imagine that there is some engagement of medial temporal lobe in visual tasks. The fantastic work by Garcia and Morgan Barenza in Toronto have shown that for certain high-order discrimination tasks, the hippocampus seems to be required. But again, not all perception, not all imagination. There are subsequent further refinements. Only certain kinds of imagination, such as self-centered future and hypothetical thinking, spatially coherent scenes, and so on. And only certain kinds of perceptual processes, abstract, featureless bindings, and things of that sort. This is just to give you a taste of how prevalent this hippocampal activity tests that are not only memory. This is my own data as a paper that we just published a few months ago. This is a robust regression on an ROI in the hippocampus where we were testing activity in the hippocampus for contrafactions that people consider more likely versus contrafactions that people consider less likely. And we get this very significant effect of increased hippocampal activity for contrafactions people consider are less likely that could have occurred in their life relative to contrafactions that they think are more likely that could have occurred in their life. So it looks as though there is a differential effect in hippocampal engagement in contrafactual thoughts as a function of their perceived plausibility. So the behavioral profile of the hippocampus, at the very least, is incredibly complex. It is way more complex than the original that the sort of simplified picture that they show us is. So we already have a lot of data, and if we have even more data, it's probably going to be even messier. So the question is, why haven't researchers in the hippocampus come up with something approximate to the operation function? Well, we have been trying. This is one paper from an issue in the Journal of Experimental Psychology General, when they asked experts in hippocampus to tell us what does the hippocampus do. And what I'm going to show you is that the 4 experts, there are like 8 there, but 4 samples in which they tell us different stories. So this is Eleanor McGuire and Molly. They say, well, the hippocampus computes, or the computation of the hippocampus is to generate spatially coherent scenes. Daphne and Nick Turk-Brown talk about 2 functions of the hippocampus. One is memory modulation, and the other one is adaptive function. And what shifts between those functions is going to be something like engagement with attention. Mark Howard and Howard Eichenbaum, they're going to tell us that Howard was at the time starting to work on this beautiful work with rats and multiplexing time and space signals in CA3 regions of the hippocampus. So his suggestion is, no, space is not only the thing that matters. What matters is the space with time. And in fact, there's a paper that just came out a couple of weeks ago from Chara Ranganathan's group showing differential engagement for spatial recognition in a virtual reality task versus episodic recognition, namely an event that occurs through time. So it looks as though it's not a space, but a combination of space and time. And of course, McLellan's work saying, well, it's something in the order of pattern completion and pattern separation in multiple memory systems. So of course that people argue about this. We researchers interested, and this is another, I didn't include the abstract, but Baranza suggests that the hippocampus codes sensory-dependent conjunctions of spatial features. So we have been trying to do this for a while. We call it the neuroscientists. To fit the many variability in data, we normally try to postulate additional intermediate and sometimes tiered subprocesses described in terms that are neither psychological nor neurological. None of these descriptions of what the hippocampus is doing is couched in terms that are either psychology or neuroscience. They are couched in terms of something like a computational model. And we disagree about what that computational model is, right? So the thought is, even if a theory-free notion of a basic brain region were somehow to become available, the computational description of its putatively associated operation function would likely depend upon a particular computational framework, right? But we disagree about the computational framework. And if we disagree about the computational framework, more data is not necessarily going to resolve it. Now, it's interesting, as I say something about the Bayesian assumption. Throughout the paper, they assume that the brain is a Bayesian machine. But that's already a big assumption in the computational framework, right? And the third point that I wanted to make is about this top layer. So we think that our data actually indexes cognitive processes or behavioral functions, but in reality what we're doing is tasks. That's what people do in scanning, that's what people do in neuropsychological tests. We do tasks, right? We never really measure behavioral functions directly, if you will. We measure tasks, performance in tasks that we think index these behavioral functions. So there is a layer between the psychological process and the task, right? But this layer is actually kind of nuanced because often, in theory, theoretically, there are conceptual disagreements as to whether a certain task measures one or another behavioral function. So one of my favorite examples, for instance, again back to HM. HM is said to have skill learning preserved. But if you read carefully the tasks that they engage in skill learning, there's one task in particular that is very interesting. It was a metal peg. It's a board with a bunch of metal pegs. I think the original array was something like 18 by 18. And HM's task, or anyone's task, is to go from the lower left side of the board with a metal stylus to the top right of the board with this stylus. Now, there is like a secret path, and the secret path is only identifiable if when you move from peg to peg, it doesn't make a noise. If it makes a noise, it's an error, and then you have to correct it. Right? They tried this. They didn't report this match because HM failed at all of this, completely failed. So what they did is like, well, maybe working memory was not a term at that point. Immediate memory is how Milner called it. Maybe this immediate memory is saturated by the time in which they're doing this task. So we have to make it smaller and smaller and smaller until they did finally an array of 5 by 5, just tiny. And there were paths that were as short as 6 pegs. So if you think about it, it's very incredibly close to zero reaction times, which is a task. So the smaller version is similar in nature at the very least to a longer version of zero reaction task, or zero reaction times, which is a task that is normally used to index skill learning. We see here that HM was incapable of doing that task, which is supposed to index skill learning. Nowadays, we think of it as being indexing skill learning. So what gives? That how we interpret the task, they didn't interpret it back then as skill learning, but now it's very similar in nature to the task that we employ for skill learning. Here's another, perhaps less contentious example. There's a lot of discussion, it might not come as a surprise to you, as to what's the difference between working memory and attention. And there's a number of researchers now that have suggested that certain tasks, like for instance, do I have that here? Oh, yeah, I have this. That for instance, that MBAC tasks are actually not tasks that are measuring working memory, but maybe they're measuring something like attention to internal representations, or even cognitive control or something like that. So the thought here is, there are these changes sometimes that happen in our interpretation of what a task is actually measuring, right? And the problem here is that if, suppose that for some magical agreement, all the researchers in working memory are starting to say, well, maybe this particular task is not really measuring working memory, but attention, then we're going to run into problem with big data. Because if we reconceive what a task measures, not because something changed about the brain or about the task, but rather because we have reconceived the nature of the cognitive or behavioral function we were supposed to measure. So this is a working memory and attention. And as a result, we end up mischaracterizing the operation function because we wrongly categorize the behavioral function it supposedly indexes. Now, big data might reduce this concern, but I don't think that it will eliminate it. Because often these local or conceptual confusions about the right sort of computational description of a putative operation function won't get averaged out from aggregative massive amounts of brain data. They end up being, because they're not really noise. It's not that the big data is going to pick up the noise. They are just the wrong kind of signal. So in sum, I have presented 3 challenges to the bottom-up approach. First one is the difficulties of identifying brain regions. The second is that the operation functions are always going to be model dependent. And the third one is that there are conceptual challenges mapping tasks to behavioral functions that might not be fully controlled for by just an aggregating over massive amounts of brain data. So what to do? And this I think is the last slide. My thought is not that different from things that a lot of people in this room have suggested. None of these approaches alone is going to work. Top-down and bottom-up approaches are probably both needed. Nobody is going to say that having massive amounts of data is a bad idea. No, of course it's a good idea. But that doesn't mean that we need to sort of eliminate the top-down approach altogether. It is important to both refine our methods, top-down methods and bottom-up methods. There are lots of, so for instance, one of my good example of refining top-down methods, cross-validation across different neuropsychological tasks. And I'm going to give you one very particular example. You also the arcade fascicle. When you have a damage in the arcade fascicle, you develop what is called conduction aphasia. And conduction aphasia makes it impossible for you to repeat. There are 2 major marks. Impossible for you to repeat things. So I tell you repeat this and then you cannot repeat it. But in addition to that, you have phonetic reading of non-phonetic words. When I was an undergrad and I was doing all this neuropsychological testing, we missed a bunch of, probably were conduction aphasias because the test for phonetic reading did not come out right. Because Spanish is a phonetic language. And we only have 5 or 6 non-phonetic words. Whereas in English, I mean, believe me, you guys, there's like so many ways of pronouncing things. And likewise in French. So if you don't cross-validate those different testings among different languages in different populations and so on, then you probably are not going to get a very good picture of the neuropsychological profile. And likewise for bottom-up approaches. So now machine learning is in vogue, and there are all sorts of different things that you can do with the data to make it better and more informative, like regularization variant or penalizing and so on. But in addition to top-down and bottom-up approaches, I think it is very important to have what I like to call piecemeal approaches, which is discussions on particular concepts and particular tasks and particular small local issues. And we need to be able to resolve local discussions. Is working memory really no other thing than just internal attention? If so, what are the ramifications of how to interpret tasks that are supposed to be measuring working memory versus attention? And those local discussions are essential if we want to solve, I think, the cognitive problems. Now, many of these local discussions will require conceptual clarifications for which I think philosophers are particularly well equipped. So hire philosophers. Thank you.
This is great. I love everything you said. I want to raise another potential problematic point, right, which is a sociological point. There's psychologists are not incentivized to agree on theories, right? In fact, the way you get famous as a psychologist is having a task named after yourself or a concept that is thought of as your concept. Nobody is famous for saying, "Oh yeah, Squire was right," you know. And so, do you see that as being a part of this, and how have you thought about how one might sort of address that issue?
Great question. Because I think that there are people in some philosophers that work, like for instance, you work in agreements in epistemology, and I think that it's an amazing issue. That there is a comparison, I forgot who made it, that theories in psychology are like toothbrushes, that everyone has its own, but no one wants to use anyone else's. Which is not true when you have children. But that's an awesome question. I don't know how to solve that issue. I think that there are at least two possible solutions here. One that is a little bit more dramatic than the other. I think that there are some very big figures in the profession that have, for ego reasons or whatever, blocked the possibility of having their theories being contested. And then there is another more, I guess, perhaps utopic. Yeah, I think I'm very much into philosophy these days. I think that there is something that neuroscientists could, or scientists in general, could learn from philosophers, which I've never really articulated that much in writing, but I think that maybe one day I will do it, which is the fact that in philosophy, they teach you to separate your argument from yourself, right? You are a mouthpiece of reason, that's how. So you can go to a talk with, I don't know, a phenomenalist about qualia or a dualist, and could be making the most preposterous, arguments ever. And then you finish, you counter-argue, and then you fight during those 2 hours, because Q&As in philosophy are super long. You fight, and then at the end, you're like friends, because it's not your fault. This is hard. And often I feel that scientists they own the result, and if the result is proven wrong, it is a personal failure when it shouldn't be. So how do I think that we could address it? Well, I think the dramatic and macabre is some people die. That would be important. And then the second, which is probably better, is to sort of help people detach, like philosophers do, the argument from the person, the result from the person. It's fine being wrong. It's perfectly fine being wrong, and it's actually should be encouraged in a way. How exactly to implement that, I don't know. But yeah, that's a great point.
Yeah, it was really great. I really enjoyed it. I'm curious. I didn't even get from the beginning how was it Gannon?
Yeah, Gannon.
Thought that what they were offering was an alternative to what we've been doing. It seemed like they were going to aggregate a bunch of papers that use exactly the methods that you said they were criticizing at the beginning. Is it just that they're hiding the methods from themselves and aggregating over it? Or in what sense were they offering an improvement? And you're suggesting the top-down and the bottom-up approach, but given the arguments that you gave, we could be coming from different computational perspectives, have different task behavior correlations, etc. Different ways of carving the brain into parts from the beginning. How, you say we should all talk about it and,
Yes.
and spend some more time trying to get clear about what
More
the
workshops.
parts are. But what I don't yet get is where the friction is going to come that's going to constrain the possible answers that we have to those questions.
Good, yeah, good point. I want to say that it is something like a continuous hypothesis testing. This is actually a very important point because the first author by proximity to job market, Bryce, my student, is here's what a philosopher call a pluralist about it. So it's like, look, there is no convergence, and there might never be convergence. We are just going to be employing different kinds of cognitive ontologies on the basis of different kinds of purposes. So for the purposes of psychiatry, one cognitive ontology might be useful. For the purposes of, for the neurobiologist, it might be another one, and so on. And I'm a little bit more optimistic, perhaps because I don't know, I'm influenced by Peirce and some pragmatists that we eventually, if we have an infinite number of scientists and philosophers working on the same issues, we will converge to the truth. I think I'm agnostic as to what is the solution. Bryce has really good arguments for thinking that I'm too optimistic. It's the Colombian in me, maybe. It might be possible that it is just an infinite amount of agreement with theory testing and hypothesis testing that will eventually get us there. I don't have a many more concrete answer. Maybe I'll end up being a pluralist at the end.
But did I understand the positive suggestion?
Yes.
It seemed to me like it was just a repetition of exactly what they were criticizing, but in big data form rather than one paper at a time.
Likely, when we read the paper, we were more enthusiastic about what it was going to say, and then at the end ended up being more confused. And part of what I've been trying to do here is to just highlight what was more confused. It's not exactly, I don't know if there is a term in philosophy for that. It's not a straw man because the paper is there, but it should have been a straw man.
I just wanted to suggest a partial answer to Professor Craver's question about where the friction is going to come from. I think the friction is going to come from whether you can actually treat patients with brain injuries, and whether you can predict behavior accurately, and whether you can modify or modulate that behavior in the direction that you want. I think that's really going to be where the rubber meets the road.
And in practical and clinical applications, it's very likely that lots of constraints are going to be there. The problem, though, is that notice that there will be situations in which no clear predictions are going to emerge, or perhaps because there are parts you won't have a patient that has a particular damage in that part of the brain, or because if that part of the brain never gets damaged alone, say. So there's still going to be circumstances in which it is not that clear what the practical implications are going to be. But I agree that that's definitely a big constraint. Sarah?
Yes, thanks for this. I think it's a clarificatory question about the academic paper, but and maybe I missed it in your presentation, but what's the criteria for, do they have a story about where the top-down categories come from? So where
They have subtitles.
Well, so I'm just wondering, so the advantage of the bottom-up was supposed to be something about their kind of a priori, that they're just there.
Yes.
And I guess that's not really the issue, because you might say, so that's how we're top-down. Think about what the mental faculties are, and it's divide them up. And so that's the reason that there's a cure in a way, and why wouldn't that work with the top-down?
Yeah, I think there might be another reason, which is, I like data-driven approaches, but it is not as if they come wearing their labels on their sleeves, right? It's not like the structure comes out of doing dimensionality reduction analysis on big data, and then they come like, oh, look at this. It's like you didn't know how to read now, but now you can read it. No, it's way more complicated than that. And I think that part of what I'm trying to highlight is that it's not that easy. The solution, that's why I call it the mirage of big data. It's not, big data is awesome for lots of reasons, but it's not going to solve all the problems. And they don't get too much into the detail when you start thinking about how big data is going to help you. There's still going to emerge, as Carl said, there's still going to emerge simulation.
Yeah, so I'm going to try try to do an analogy to genes, as I sometimes do, genotype-phenotype relationship, and then just kind of see how you respond. So if you were, if you're just thinking about the relationship between like one gene and a phenotype, like a gene and like then having long hair, there is some like mechanistic relationship between those. Like it makes something secrete keratin for a certain amount of time longer, right? So your hair's longer. But if you just had an understanding of hair, the relationship is just kind of completely arbitrary from your initial understanding of the phenotype. Genes aren't really about blue eyes, or even how a gene is used in the liver and the brain, so it's not really about whatever goes on in the liver and the brain, it's just a protein, right? And I'm curious, it could be that the relationship between brain regions and our cognitive, from top down defined cognitive categories are like that. They make a causal contribution, but it's not neatly interpretable in terms of that cognitive function, right? And so it seems like, the polyhedron you said, where they interpolate it on task maintenance for the anterior cell, right? There's this stage where you have to kind of judge as a human being what you think the similarity between these 12 things are. And I think the 4 researchers that you were talking about when you moved to hippocampus, it's like their polyhedrals are better, they've kind of got it down to 6 things, and the things are more well-founded, but they still are making that leap in the abstract where they're kind of guessing what they think ties all of these tasks together. And I don't know, it just seems to me like if the relationship between brain regions and cognitive functions is sort of as arbitrary as the relationship between single genes and phenotypes, then that strategy of a person saying what's similar between these tasks is just not going to be successful. So I was just curious how you respond to that analogy.
Great. I think that there are 2 points there. So the first point that I was going to say is that what you're saying reminds me of issues that you have when you do factor analysis in statistics, right? So sometimes you find these issues in which, depending on your rotation, you end up with different variables loading onto one factor or to another factor. And it is sometimes a little bit complicated, a little tricky. It's like, is this really a factor? Is not a factor? Sometimes you see this different loadings are not so clearly. In my lab, for instance, we try when things like that happen. You try different dimensionality reductions to see if there is agreement. But often, what this gives you is loadings similar to what is that, but you have to interpret them. And this ties out with the second question is, what are the constraints on the interpretations of those loadings? And I think that that's a really difficult question, because I think that there are two constraints of how people should go about interpreting those loadings. One is we need to have agreements of computation of what's the right computation or the computational model that these loadings are supposed to be sort of referring to. And that is something that is not going to come from the data. It is going to come from, I think, discussions and really thinking about the explanatory power of each individual model and so on. And then there is the second part that I almost don't want to say, but I think I want to say it, is that we're talking about functions, and functions have some sort of normativity to them, right? And you need to get clear what is exactly what you're meaning by function. Is you're meaning something, what is the contribution that it is making to the organism? Why is it evolved for a particular purpose? And when you unlike the hair case, which doesn't seem to be terribly normative, when the predicted variable is something that has some normativity to it, like function is, I think gets, and I'm gonna make a horrible pun, things get hairy. So when function and the normativity gets becomes the predicted variable, I think that will be it. So there are these analogies because hair is not like cognitive function in the sense that hair does not require or operant function. Hair does not require a computational process framework, and second, it might involve some normativity to it. But yes, I have time for another question, right?
Super interesting. Thanks for that talk. So I guess this is is following upon Carl and Joe's questions there. And I just, it seems like you have this criticism of this research program, and then in some ways your positive proposal is about how to carry out the aims of it better. And I think anyway, there's a gesture at another possibility, which is that we should have a different picture of like a permanently fragmented ontology of the brain, where we might find measures that localize functions in brains that are reliable in the sense that we can repeat them, and they may even be things that we can intervene upon. But this other thing where we expect somehow them to all fit together with the other measures that are also reliable and intervenable upon in order, and we get some big picture and say, oh, that's how it works. That never ever happens. And there are a lot of other areas in the human sciences where it seems like you just think it's very hard to put things together. In clinical psychology, there's this sort of famous thought that there are all these kinds of therapy that work, that they're totally inconsistent theoretically with one another, and no one knows why. Or in exercise science, like people don't even agree, like, should you lift 10 times in slow motion? Should you lift 30 times? Or whatever. Could you want to get strong? So there's all these kinds of human science questions where we don't get this sort of, even when we got a lot of data and smart people thinking about it, where everything doesn't come together. And I just think maybe this is actually your opponent. You're actually on the same side as against this picture. You're on the same side as the people you're criticizing. And I guess I'm interested in what you think about that idea, whether you would think about that as an opponent, and why so?
Good. So I don't see them as the opponent though. I see the view, and it's kind of what I think. Correct me if I'm wrong, but the view that you're suggesting is that there is this pluralism, right? In social sciences there's this pluralism, and sometimes the pluralism is like so vast that you might even have ontologies that contradict other ontologies, right? I don't see that as the enemy, because I think that Gannon and Al really don't like that view. They really definitely think this is going to converge. There is going to be convergence, and their suggestion is that the convergence is going to be pretty quick once we have a lot of data, basically. So I do see that view as let's call it like my contender according to this. And what Carl was suggesting is, so what's the difference between that view and what I'm suggesting? Well, my view is convergence, but it's slow down convergence. It is like, it's gonna happen in the long run, but this is not gonna be enough. So perhaps my opponents, if you want, is something like that pluralism. Maybe I should just turn to the dark side and become a pluralist.
Or the light side, if you think about it.
Is that, yes, right. So this is something I have to think more carefully, because I think that's a real important question. Do I want to embrace something like a pluralism of cognitive ontologies, or do I still stick to my hopes that there will be maybe in the long run convergence, and all we have to do is be more careful at each step? I'll think about that. That's a good suggestion.
Yeah, I enjoyed your talk a lot. I wanted to ask why, I saw that when you were presenting your own view, I had a question with that. You thought one of the things we should do is sort of resolve the issue of brain locations of areas. I'm wondering why you're so committed to that. The analogy I'm thinking of, I think maybe this one Joe mentioned, where when they tried to study proteins, structure of proteins, they thought of them as static. Then they realized that they're changing all the time. And I'm just thinking that James starts out his principles of psychology about hot debates about our brain functions localized. And he ends the book with saying that, or he ends the project with saying that he thinks he hasn't done much, but the one contribution he's made is to come up with I guess we call it ontology, which is a brain state. And so I'm just wondering, rather than giving my own view, I'm just wondering why what's your reason for being so committed to thinking that there are ideas, that there are localization functions, that is the way you put it?
Good question. So my commitment is not so much with, there might not be specific brain areas, but I don't know, I don't think that we have really good reason to think that something like the anterior insula is going to be a brain atom. It might be possible that it is, but I don't think that we have really good reason. And the reason for that is because the more I learn about neurobiology, the more messy stuff gets down there. Like really, really messy. And I am a mechanistic through and through. Maybe I have been influenced by some people in the audience. And I absolutely love neurobio. And I study as much as possible neurobio. And the stuff that we are discovering, as we in humankind, discovering about the neurobiological underpinnings of massive amounts of neurons is just staggering. So just to give you an example, I think, how to say it in writing, but I don't think that we have really good reason to believe that only accent potentials are the relevant neural activity for cognition. There's a lot of other stuff that happens in neurons. I don't think that it is true that the only way in which neurons communicate, and not me, lots of people think it's not true that synapses are the only way in which neurons communicate. There are neuronal gap junctures in which axons communicate with one another and they exchange enzymes. Recently, there were 2 papers that came out this year that were fantastic on RNA transmission, non-synaptic transmission of passing from pre-cellular membranes to post-cellular membranes are RNA signals without there being synaptic. So there is an enormous amount of stuff that we don't know even at that level. And I don't need a definition of what a basic brain region is, but I need a very good reason for thinking that a putatively brain region is really a neuronal. And think about glia, like the stuff that, didn't they discover G32, the other kind of glial cell that was like hiding between glial cells? And there is this researcher Edelman, I think, in the NIH that works on the cognitive import of glial cells, and there is a lot of that level that we really still don't know. So that's my concern, not so much with definition as with the reasons as to why we think that a putatively brain region is really a neuron.
Oh, okay, so I mischaracterized what you're related to. Okay.
All right, thank you very much.